Hi, in this video, I'll be going through the properties of the ideals that we have introduced in the previous video and end off with talking about what is a maximum ideal and a prime ideal. And so let's now begin with properties of ideals. And so now we define the sum of two ideals to be A plus B for all A in the ideal, B in the J ideal. And the product to be the set of all finite sums of forms AB. So this equals to the sum of AB, where A is an element of I, B is an element of J. And the nth power is just of the form A times all the way to AN. And then all these AIs are an element of I. Or you can just define it inductively. So the reason why we can define all this is because it's an ideal, so it's really well defined. And we can actually see that the sum I plus j is the smallest ideal of R containing I and j, and that ij is an ideal contained in I intersect j. And the elements of the product ideal are just are finite sums of the product elements of AB from I and J respectively. And so the set AB of this consisting of products is not closed under addition. So in general, it's not an ideal. So you really need it to be the set of finite sums. So some examples of ideals, and when you add them is, for example, you have the ideals with multiples of 6 and multiples of 10. When you add them, it consists of all integers of the form 6x plus 10y. And since every such integer is divisible by 2, I plus j is contained in the even integers. And because 2 equals to a linear combination of this, you also can say that this ideal contains the ideal of 2. So in that sense, 6z plus 10z equals to 2z. And in general, you can add the two mz plus nz and it equals to dz, where d is the GCD of m and n. And the product of the ideals is clearly the 6. It just gives you 6 times 10 z, which is just 60z. And so if we let I be an ideal of the polynomial rings with integer coefficients, we can see that the polynomial 2 and z are contained in I. And so 4 and x squared is contained in the product ideal, I squared. And so is their sum. But you can see that now the sum cannot be written as a single product of PQ times QX. So you really need you can see how you really need the set to have the finite sum property to be defined in the finite sum sense, so that it is still an element of the ideal. And then we denote an ideal generated by a set as the following. So it's all the set of finite sums first of all, and you can actually just check that it's just R, A, R. And then this is actually just the intersection of J, where J contains A and J is an ideal. So it's really the smallest ideal that is generated by A. And then we can denote RA as the left ideal generated by A and AR as the right ideal generated by A. And you can check that they are ideals. And we say an ideal generated by a single element is known as the principal ideal. And it's really saying is the sum of is just capital RA times capital R at the back. And any ideal generated by a finite set is called a finitely generated ideal. So some examples is the zero ring is generated by just one element 0, and R is generated by all the elements multiplied by 1. So these are principal ideals. And we can check that the ideal generated by N is the principal ideal of Z. But you can also see that there are ideals that are not principal. For example, the ideal generated by 2 and x. So this set 2 and x, the ideal generated by them is not principal. And because 2 and x contains all linear combinations of 2 times px plus x times qx for p and q as an element of the set of polynomials with integer coefficient, if we assume that it is principal, then it must equals to some ideal generated by some element in this ring. And so since 2 is an element of this ideal, it must have some px such that 2 equals to px times ax. But then you see that the degree here is 0, and so the degree here and here must be 0 also. So this and this must be constant. And since we know this 2x don't generate the whole thing, ax cannot be 1, so px must be 2. So this means that ax is a constant polynomial 1. So the only possibilities in this case is that ax is 2, because ax cannot be 1, so ax must be plus minus 2. But because we know x is an element of this ideal 2, then x must equal to 2 times some polynomial q. But that's not possible because the coefficient of x is 1, which is odd, and the coefficients everything on the right hand side will be even. And this gives a contradiction that 2x is not principal. And we have more properties that we can prove that help us determine when an ideal contains a unit, or when an ideal equals to the whole set, or when a ring is a field. And so the ideal equals to the whole ring if and only if I contains a unit. And that's very easy to check, because if I equals to R, then of course I contains the unit, so that's very trivial. And conversely, if U is a unit in I, then it has an inverse, and for any R, it must equals to R times 1, which equals to R times VU. And then you use the associativity to put the brackets at R times V times U, and because U is an element of I, this whole thing will be an element of I as well, and hence R equals to I. And to prove it's a ring if and only if every non-zero element is a unit, and if R is a field, then every non-zero ideal contains a unit, and so by the first part, R is the only non-zero ideal, and we are done. And conversely, if 0 and R are the only ideals, then we let U be an element of R. By the hypothesis, the ideal generated by U must equals to R, and so 1 must be an element of this ideal, and so it must be a unit, and hence every non-zero element is therefore a unit, and so R is a field. And by this corollary, it shows that a field with any ring homomorphism will be injected into another ring. And the kernel of this ring homomorphism is an ideal, which has to be the proper 1, 0. And so this shows that our ideal structure of a ring is trivial. So really, when you have a field, then the ideal structure is just the 0 ring or the whole ring. So it's trivial. And we define an ideal to be the maximal ideal. Firstly, it must not be the entire ring. This is important because if it can be the entire ring, then S will always be the maximal ideal. So it needs to be proper first of all. And the only ideals containing M is just M or S. So no other ideals is bigger than M except the whole ring. In general, a ring need to have a maximum ideal, and you can just take any abelian group which has no maximum subgroup, such as in the rational numbers, and you can make this a trivial ring by just defining multiplication equals to 0. But what we want to say now is if the ring possesses an identity that is non-zero, so it's 1, then it must have a maximum ideal. And that's the use of Zorn's lemma. So in that case, Zorn's lemma is a bit more technical. I'll leave it to you to read in the textbook. So what it says that if you have a ring with an identity, then every proper ideal is contained in some maximum ideal. So a maximum ideal always exists in this ring. And now what we can say is that if R is commutative, then an ideal is maximal if and only if the quotient is a field. And a quotient is a field if and only if the only ideals in this is the 0 and the whole ring, R over M. So how we prove this is that it actually follows from the lattice isomorphism theorem, which is basically isomorphism theorem number 2, and isomorphism number theorem number 4, and ideal is maximal if and only if there's no ideals containing it. And so the ideals of R containing M corresponds to the ideals of Rm. And so M is maximal if and only if the only ideals of this thing is 0 and Rm. So we see that this follows that because this holds true, Rm must be a field. And so M is maximal if and only if the quotient ring is a field. So this gives us a way of constructing fields, as we just need to take a quotient of a commutative ring by a maximal ideal, and you get a field. And we'll see examples of it. So the ideal of nz is maximal if and only if this is a field. And we know this is a field because it's the finite field of n elements, and hence this ideal is maximal. And we can see that 2x is maximal because its quotient is the field z over 2z. The principal ideal z is not maximal because now this ideal generated by x is contained within 2x, which is contained in the polynomial ring. And so when you quotient it, it's not going to be a field, and instead you see that when you quotient it, it's just going to be z. And this also gives us another way to see that it is not maximal, because when you quotient it is z and z is not a field, so you know that the ideal generated by x is not maximal. And now we define what a prime ideal is by saying that if you are the product of two elements a, b, then at least one of the elements must be in P. Another way of saying it is that if A is not in P and B is not in P, then AB cannot be in P. And this is a generalization of the prime notion in your integers, where an ideal Iz is prime because of this, and provided every time the product AB is an element of nz, at least one of the elements A and B must be an element of nz. And this is just saying that if n divides AB, n must divide A or divide B. And this our definition of prime. And so the primes of Z are just the prime ideals generated by some prime element. But it's not true. And then we see that in integers, our maximum ideals and prime ideals are equivalent. But it's not true in general. And so we need to think of when we will now go on to say when a prime ideal is when a maximum ideal is prime. And first we need to prove that an ideal is prime if and only if the quotient is an integral domain. And so the proof is simply a matter of translating the definition of prime ideal in the language of quotients. And we are saying that an ideal is prime if and only if AB is an element of P, then A is an element of P, or B is an element of P. And we take the quotient, it is saying that R is an element of P if and only if the remainder is 0 in the quotient of Rp. And so in this sense, P is a prime ideal if and only if whenever AB quotient equals to A quotient, B quotient, then either A quotient equals to B 0 or B quotient is 0. And this is saying that Rp must be an integral domain. So you can see how it is really based on definition only. So in particular, a commutative ring is an integral domain if and only if 0 is a prime ideal. And by that, a corollary will be every maximum ideal is prime. And we see that if M is a maximum ideal, then the quotient is a field, and since fields are integral domains, it must be that M is prime. And so some examples of prime ideals will of course be the principal ideals generated by primes in integers. And we can actually check that the ideal X is prime since when you quotient it, it's an integral domain. However, we already shown that this ideal is not maximal, and so we have found examples of ideals being prime but not maximal, even though every maximal ideal is prime. So that's all for this video. I hope you have enjoyed it. Please like, share and subscribe, and I'll catch you in the next one. Bye.